Welcome back. Today we're going to be talking about experimental probability. Our content objective is students will be able to calculate the experimental probability of an event. The language objective is students will be able to describe what experimental probability is. And why am I learning this? Well, it's important for real-world problems like 40% of people polled voted for a certain candidate. Background knowledge. So we talked about how probability could be expressed as a fraction between 0 and 1, or how it could be expressed between 0 and 100%. 0 being impossible, and in this case, 1 being certain or 100% being certain. An event is the experiment is the activity that we observe. So, for example, some examples may be the experiment could be flipping a coin, rolling a number cube. The outcome is one of the possible results of the event. The sample space is all the possible outcomes for the experiment. So the sample space for flipping a coin is heads and tails, and the sample space for rolling a number cube is 1, 2, 3, 4, 5, 6, because those are all the possibilities. So probability describes the likelihood that an event will occur. The theoretical is the number of desirable outcomes over the total number of outcomes. Theoretical probability is what should happen, is what we expect to happen. So what is typically on a standard coin? Well, the event is flipping a coin. The sample space, again, is all the possible outcomes, so it's going to be heads or tails. Theoretical probability, as a reminder, it's the number of desirable outcomes over the total number of outcomes. So find the probability of each event. What's the probability of it landing on heads? Well, let's see. Our sample space is heads or tails. That's the probability. Those are the different outcomes. And we're looking specifically at heads. So we would say 1 out of 2. So heads being 1 out of the 2 sample space. Well, what's the probability of flipping a tails? Same idea. Here, 1, we can have tails, but out of 2 different possibilities, so we would say 1 out of 2. Now, what's the probability of flipping feet? Well, hopefully you know that there's no way to flip a coin to land on feet. So we're going to say 0 out of the 2 possibilities, which is heads and tails. So that's 0. We would call that an impossible event. So what numbers do you see on this number cube? Hopefully you first understand that the event would be rolling a number cube, and the sample space would be all the different numbers you can roll, 1, 2, 3, 4, 5, and 6. Theoretical probability, again, looking at what we're looking for, what outcome are we looking for over how many outcomes were there altogether. So here, what's the probability of rolling a 3? Well, we got to look again at our sample space. There's these different possibilities, and the only one that we're looking for is 3. So this is going to be 1 out of a total of 6 different outcomes. Okay, what's the probability of an even number? Well, we're still looking at the same exact sample space, 1, 2, 3, 4, 5, 6, but we're specifically looking at the even number, so 2, 4, and 6, which means that is 3 out of 6, which reduces to 1/2. Now, what's the probability of rolling a 1 or a 6? Again, the sample space is exactly the same, but now we're looking at 1 or 6, so we would say 2 out of 6. But remember, we can always reduce fractions, and whenever we can, we should. So that's going to leave us with 1/3. If you're wondering how I'm getting these reduced fractions, I'm just simply dividing the numerator and denominator by a common factor. Here in this case, it was a 2. 2 divided by 2 is 1. 6 divided by 2 is 3. Okay, what's the probability of rolling a 9? Well, our sample space is still 1, 2, 3, 4, 5, 6, and from the looks of it, there are no 9s at all. So I'm going to go ahead and say that's 0 out of 6, which is 0, which again, this is an impossible event. So let's remember with theoretical probability, we're looking at the number of desirable outcomes over the total number of outcomes. So here, probability of heads is 1 out of 2, and then probabilities of tails is also 1 out of 2. But do you think if you were to flip a coin 100 times, exactly half of those flips would land on tails? And how about half exactly landing on heads? Well, let's go ahead and do a quick demo and see if that actually happens. Okay, but first let's understand what we're doing. This is called an experimental probability. It's basically obtained by doing experiments. So each experiment is called a trial. And so experimental probability is slightly different. We are looking at the number of times the event occurs based on the number of total of trials. So here we have a table. We're going to go ahead and use this table to fill out our results from a quick demo. So here we're going to go ahead and do 100 tosses and see what that gives us. Let's go ahead and arrange in a table so we can quickly see our results. Okay, so now that we have all this information, we're just going to go ahead and fill it in. Okay, so here we rolled it 100 times. 59 out of 100 were were heads. That's going to be 59 hundredths, which is then 59%. If you're wondering how I was able to convert that into percent, there's two ways I did that. One way is to understand percent is per 100. How much was it per 100? It was 59. And the other way was to go ahead and move the decimal over 2 places to the right, giving me 59%. So that works as well. Okay, so what about theoretical probability? Well, we'd expect heads to be rolled once out of the 2 different outcomes. So I would go ahead and put 1/2. Okay, so now moving back to tails. Well, tails was 41 out of 100. So that would be 41 hundredths, which is then 41%. And yet again, theoretically, we expected it to occur 1 out of the 2 different outcomes. So we would write 1/2. Okay, so remember theoretical probability is the number of desirable outcomes over the total number of outcomes. The probability of a 3 was 1/6, and the probability of a 6 was also 1/6. So the question is this: do you think if you were to toss the number cube 100 times exactly, 1/6 of those tosses would land on 3? And how about exactly 1/6 landing on any number? Well, let's see. Again, we're going to go ahead and do a quick demo. So here we're going to go ahead and roll it 100 times and see what our results gives us. Okay, so here's what we have. A 1 was 17 out of 100 times, which is 17 hundredths and 17%. But theoretically, we expected it to occur 1 out of 6 times. A 2 was 16 out of 100, which is 16 hundredths, which then turns into 16%. But again, theoretically, we still only expect it to occur 1 out of 6 times. A 3 was 19 out of 100. This is 19 hundredths, which is 19%, and theoretically 1 out of 6. A 4 was 12 out of 100, which is 12 hundredths, which is then 12%, and that leaves us with, once again, just still 1 out of 6 theoretically. A 5 was 15 out of 100, which is 15 hundredths, which is then 15%. Theoretically, we expected it to be 1 out of 6. And last but not least, 6 was 21 over 100 out of 100, so it's 21 hundredths and 21%. But yet again, theoretically, 1 out of 6. So notice these percents, okay? Notice if you were to, they are pretty close to 1/6, which is about 16.7%, okay, most of them, with the exception of 4 not being rolled that often and 6 being rolled pretty often. Okay, so now on to the next, which in this case, the event of spinning a spinner. And what is the sample space? Well, we have different colors. We have yellow, blue, purple, red, and cyan. So we're going to go ahead and complete this chart here, just like the previous demos. So here we go. We're going to go ahead and spin it 100 times and see what this gives us. I'm just going to skip to the end real quick, and here's what we ended up with. Okay, so let's fill this in. For the color blue, it occurred 18 out of 100 spins, which is 1800, which is 18%. But theoretically speaking, we expected it to occur 1 out of the 5 different outcomes. What about yellow? Yellow occurred 19 out of 100 spins, which is 1900ths, which is 19%. But again, theoretically, we expected it 1 out of 5. Cyan occurred 22 out of 100, which is 2200ths, and 22%, which is 1. Still theoretically 1 out of 5. So notice, theoretically speaking, that doesn't change. Okay, so red was 18 out of 100 spins, which is 1800ths, which is 18%, which again theoretically is just 1 out of 5. And last but not least, purple was 23 out of 100, which is 2300, and then 23%, but still just 1 out of 5. So the law of large numbers states that the more trials you perform in experimental probability, the closer you get to the theoretical probability. Okay, so first let's just assume we only spun it 10 times. Let's see the experimental probability versus the theoretical probability. So here we go. For 10, here are the results. 40% of it was blue when we expected 20, 10% of it was yellow when we expected it to be 20. Cyan was right on the dot, 20%, 20%. So was red, but purple was a little short, only 10%. Okay, now let me reset it real quick. Now let's do 100 like we did in the previous demo. So notice these numbers are all of them are pretty close to 20, with this exception here. This one being a little bit too much. Okay, but again, it's going closer to the theoretical probability. Now I'm going to go ahead and reset it one last time and go as much as I can, which is 1000. Okay, so notice it's they're all getting really close to 20. But let's continue to spin another 1000. And another 1000. Okay. So here, the results are getting closer to 20. I'm going to go ahead and spin again. So now we're at 3000. Ooh, notice it's getting a lot closer to 20%. Let's spin again. And again, it's going to continue. So just like the law of large numbers states, the more trials you perform in the experimental probability, the closer you actually get to the theoretical probability you should get. Okay, so now, in the following experiment, a marble is randomly drawn out of a bag and then replaced. The table shows the result after 50 draws. Find the probability of drawing a green marble as a fraction, a decimal, and a percent. So what is the event? Well, the event is drawing a marble out of a bag. What is the sample space? Well, there's 3 different possibilities. It's green, red, and yellow. So that is our sample space. So the probability we're doing is the number of green marbles drawn comparison to the total number of marbles drawn. So here it's 12 out of 50 because we pulled out 12 out of total of 50 of them, 50 draws. So this probability of drawing a green marble is 6 out of 25. Why? I went ahead and reduced this fraction here by 2 since I noticed both of them were even, leaving us with 6 over 25. Converting that into a decimal, it would be 2400ths, and as a percent, it is 24%. If you're wondering how I did that, all you would have to do is do 6 divided by 25, and that would lead you to 2400. So remember from a previous lesson, we talked about how we can create equivalent fractions. We showed a model, and then we split the model into smaller pieces and showed how it could be expressed with a different denominator. Now, if we assume that each marble color will continue to be drawn out at the same rate, how many green marbles would you draw if you draw a total of 100 marbles altogether? So here's our probability so far. 12 out of 50, for green, 24 out of 50 for red, and 14 out of 50 for yellow. So taking a look at green, okay, it's 12 out of 50. But we want to know how much would we expect to see out of 100. Well, we're just going to go ahead and manipulate the process by multiplying the denominator by 2 because 50 times 2 gives me 100. So I'd expect this to double as well, which gives me 24. So my answer is I would expect there to be 24 green marbles. Okay, so if we assume that each marble color will continue to be drawn at the same rate, how many green marbles will you draw if you draw a total of 350 marbles altogether? Well, we're still going to use this probability of 12 out of 50, except now our total is not 50, our total is 350. How does that work? Well, 50, in order to get to 350, would have to be multiplied by 7. So I'm going to go ahead and multiply the numerator by 7 as well. So 7 times more draws, 7 times more greens. So 12 times 7, I'd expect there to be 84 green marbles. So now, how many red marbles would you draw if you draw a total of 25 marbles altogether? Okay, so taking a look at red, okay, we have 24 out of 50. But instead of pulling out 50, we're only pulling out 25. Well, think of it. Well, if you're pulling less marbles altogether, we expect less of them to be red. Specifically here, it was half of it. Half of the total means half of the reds, leaving us with 12. So there are 12 red marbles. That's what we'd expect. So notice how I'm using these probabilities to make an educated guess. Next, how many yellow marbles will you draw if you draw a total of 125 marbles altogether? Okay, so yellow, we have 14 out of 50. Okay, and now the total is going to be out of 125. What could I multiply 50 to give me 125? So now you're going to notice this one's not as easy. I can't figure out 50 times what gives me 125. So I'm going to use a variable. I'm going to call it n, because I'm going to try to figure out what this multiplier is. Okay, so here I'm going to set it up as 50 times some number n is going to give me 125. So I'm going to go ahead and divide both sides by 50, leaving me with n equals 125 divided by 50. So I'm going to do some side work. 125 divided by 50. This can't go into 1, can't go into 12, can go into 125, 2 times with the remainder of 25. Bring down that 0. Okay, 50 goes into 255 times. So this was not a nice whole number, but I figured out that we would have to multiply 50 by 2.5 in order to get us 125. So I'm going to change this n to 2.5, which means in order to figure out this number, I'm just going to also multiply it by 2.5. So some more side work here. Let me just make some more room. I'm going to go ahead and multiply 14 by 2.5. It's going to be 20, 7, 0, 8, 2, 0, 5, 1, 3. Move the decimal over once. So I'm actually going to say that there is 35. So I'd expect there to be 35 yellow marbles. So notice this skill here. You are going to be using that later down the road in 7th grade. It's called the constant multiplier, and it's a very good skill to have. So it's good to understand how it works. Well, guess what? That's going to conclude the lesson for today. Thank you so much for tuning in, and as always, until next time, bye!